Okie dokie, so this video is basically just going to be to show you how the kinematics can be taken from the simple motion equations you've already used in previous years. By that I'm talking about V equals delta D over T and A equals delta V over T. So from these equations we can actually get much more impressive equations which are able to allow you to figure out a lot more. So for example, if you just had the initial and final velocity and the time, you would be able to figure out either the distance or the acceleration. Or if you had the final velocity, the initial velocity, and the acceleration, you'd be able to figure out the time. Or initial velocity, distance, acceleration, then you can figure out time. All of those kinds of things, you can. It just expands how you can figure stuff out. On top of that, these equations are designed for either the same velocity the whole way through or a linear change in velocity. Whereas the kinematics allow for where it's not so tidy. So the variables we have, we've got delta D. Now we're going to keep that delta there, even though I'll show that delta can be used in other ways. We're going to keep this here because it works as is. Now delta D is the change in displacement. Now remember, displacement is different to distance. Distance is how far you are from the point where you started. Oh no, sorry, that's displacement. Distance is how far you have traveled regardless of your initial point. So you could go around in circles around your starting point and your distance is going to keep going up and up and up and up and up and up and up. However, your displacement wouldn't, because you're the same distance from your starting point. We've then got V, which is velocity. We've got A, which is acceleration, and we have T, which is time. And might as well put this in. So the units that you use for these are going to be meters per second, and meters per second squared, or meters per second, and then seconds. So that's what you've already got. This part's sort of just a recap. Now something to consider. Let's look at the velocity in both of these equations. So in the top equation with distance, what we're actually looking at is the average velocity. Now, this word average is important here. The average, mathematically, is going to be sum of all of your values, and then that's going to be divided by the number of values you have. So let's say I wanted to get the average height of an entire class. I would record every single person's height, and then I would divide the sum of everyone's height, or everyone's heights added together. I would divide it by the number of people in that class. So we've got the sum of values and divided by the number of values. So in the case of velocity, we're basically going the initial value plus the final value. Now that means that getting the average between those 2 points, we're just dividing by 2 because we only have 2 values. Now that's splitting velocity into initial and final, which is perfectly okay. That's what I was meaning where this allows for not necessarily linear changes in velocity. And then we can have a look at the other equation, the acceleration. That one is the change in velocity. And so that change in, that's a little bit different to average. Change in is going the final value minus the initial value. And that's what the change in something is. So in the case of velocity, that's going to be the final velocity minus the initial velocity. Now we add these into these equations and we start to see quite a few interesting things. So just going to make this all a wee bit smaller. Probably won't be able to read it, but hopefully you'll be able to sort of remember that it's there. And we're going to get rid of the big old title. And we're going to bring in sort of this kind of area. I'm just going to, all that wonderful formatting. There we are. So, there are 4 kinematic equations, hence the 4 boxes here. So, our first one, we're going to look at putting in what we've just figured with the whole average velocity thing into v is equal to the change in displacement over time. Now that's the average, so if we just substitute that average in, we end up getting vi plus vf all over 2 is equal to the change in distance over time. Now if we want to just have one variable by itself, let's say the distance, we can then multiply both sides by t, so we have vi plus vf over 2 times t equals the change in distance. Now this here, this is the first equation. It means we don't have to worry about any sort of acceleration. We can figure out what the initial velocity is, what the final velocity is, what the time, or what the distance is, as long as we have the other 3. Now we can do the same again with the acceleration equation, because we figured out what change in basically means for the velocity, and well, for anything, but we're focusing on initial and final velocity here. So if we substitute in what we got for the change in the velocity, we end up getting acceleration is equal to the final velocity minus the initial velocity all over time. And we can keep that. We've now got one thing as the subject, one thing as the focus of the whole equation, and so we can stick with that. We could, if we wanted to, rearrange it to have the final velocity as the subject. I'm just going to do that because that's generally how it's written down. But realistically, you can rearrange any one of these equations to make any one of the variables in them the subject. So for this, we would multiply a by t so that we then get Vf minus Vi, and we don't want to have negatives and stuff, so it does kind of make sense to make the Vf the subject, because we end up getting At plus Vi is equal to Vf. And that's how it's usually written. Now the question is, well, how could we possibly get the other two kinematic equations given that we've just used the two equations we know? It does get a little bit fancier, but it's still perfectly possible with the level of maths knowledge you guys probably know. Rearranging and all of that is a really important tool, and being able to come up with new equations, all it really ever usually is taking existing equations and mixing them together. So we can look at these two equations, and so let's say we want an equation that means we don't have to worry about time at all. The way to get rid of that is use two of these equations that we've just figured out, make time the subject, make time the important part of it, and make them equal to each other, and then we get rid of time. It's like simultaneous equations kind of thing. So we'll do that for time. So we've got Vi plus Vf over 2 times t equals the change in displacement, sorry. So if we multiply by 2 and divide by the Vi plus Vf, we'll end up getting t by itself. Multiply by 2, divide by, anyway. So basically we take this fraction, we flip it upside down and bring it to the other side. So we end up having t is equal to 2 delta d over Vi plus Vf. So we've now got t as the subject. We can then look at the other equation. So we have At plus Vi equals Vf. So we go backwards to what we had before, where it was just At on one side with Vf minus Vi. And then we divide through by a so as to get t by itself. So t equals Vf minus Vi over a. Now these are our two equations, and because they both equal the same thing, we can say that they are equal. Because if I say that equation A is equal to 1 and equation B is equal to 1, that means they're both equal to 1, therefore they are equal to each other. So we end up having 2 delta d over Vi plus Vf is equal to Vf minus Vi over a. Now the first thing we want to do is get rid of the fractions, so we cross multiply, so we take whatever's on the bottom and we then multiply the other side by that. We're multiplying by both sides, but obviously if you multiply something while you're dividing by it, it goes away. So like if you had 1 divided by 2 multiplied by 2, that's going to be 2 divided by 2, which is just 1. So yeah, we cross multiply and we end up getting 2a delta d equals Vf minus Vi and Vi plus Vf. Now, something you may have come across is a thing called conjugate pairs in like quadratic equations and stuff. Basically it means that it's going to turn out quite nicely, and we're just going to get the squared values as opposed to the bit in the middle, which is a messy combination, and that's just because of the plus and the minus, but you don't need to know about that, so we will leave that as is. So we have Vf times Vi, then we have negative Vi times Vi, so that's minus Vi squared. Then we have Vf times Vf, so plus Vf squared, because it's Vf times Vf. And then negative Vi times Vf, which is negative Vf vi, which means that these two cancel out and these two remain. So we end up getting 2a delta d equals vf squared minus vi squared. But again, we don't want that minus in the equation, so we just move that over. And we end up getting 2a delta d plus vi squared equals vf squared. So here we now have an equation which can be used regardless of whether or not we have time. Time does not factor into this equation. Now, for the final equation, you're probably thinking, oh, well, vi and vf are in all of these. I'm just going to do the version which doesn't have the final velocity. However, you could do the exact same thing to get one that doesn't have the initial velocity, but often the initial velocity is either a known value or it's 0. Because generally speaking, you know where something started from. And like, you won't need the equation that just uses vf instead of the v0, vi. So we'll just do the one with which gets rid of the final velocity. Now we're going to ignore this last equation just because it has squares and stuff and it gets messy. Now this equation here, the at plus vi equals vf, now that's already got the subject being vf. Therefore, we don't need to change that one. The other equation, however, we do need to change a little bit. So we have vi plus vf over 2 times t equals delta d. So then we move that, so we can again cross multiply, kind of like getting rid of the fraction. We divide both sides by t to get that t onto the other side, and we multiply both sides by 2 to get rid of that fraction. So we end up getting this delta d, vi plus vf, we end up getting this delta d equal to 2, the delta d side to be equal to 2 delta d over t, and then we just need to move the vi over, so we have vf is equal to 2 delta d over t minus vi. And so now we've got our two equations, so we can do the same again when we mix them together. So we end up getting at plus vi equals 2 delta d over t minus vi. Now we want to get all the like terms together, so easiest option first is to just add vi on both sides so as to get rid of the negative vi and get it on the other side. So we end up having at plus 2 vi, which is equal to 2 delta d over t. And we want to multiply by t so that we don't have to worry about having that fraction. So we have at, and t times t is t squared, and then plus 2 vi t, which is equal to 2 delta d. Now, so as to get the delta d by itself, we just divide through by 2. So we end up getting 1/2 at squared plus, and 2 divided by 2 is just going to be 1, so it's going to be vi t, which is equal to delta d. And that's our last equation. And again, like if I had rearranged those two first equations to make vi the subject, we could have gotten rid of vi. However, you don't need to know that one at the moment. You are welcome to have a go at figuring it out yourself. But the big important thing is understanding what equation is for what. So our first equation is for when you don't have acceleration and you're not looking for it. The second equation, and I'm going left to right, top to bottom, the The second equation is for if you don't have displacement and you're not looking for it. The third equation is for if you don't have time and you're not looking for it. And the final equation is for if you don't have the final velocity and you're not looking for it. And so with these four equations, you can figure out basically any sort of motion problem that has a constant acceleration. That's the one big thing. Acceleration must be constant, or else you're calculating the average acceleration. But to open up that question would be a whole different thing and would require a whole heap of other considerations. But yeah, hopefully this was useful. I would recommend having a go at deriving them yourself, because it is a handy one to do. And if you know how to manipulate these equations, any sort of calculations with this will become a lot easier. But yes, have a good day.